And it's really interesting because we still don't know, here at the end of 2019, we still don't know what the fate of the Earth is.
Today, I welcome back Professor Ethan Siegel, an astrophysicist. He's a former professor at Lewis and Clark College, a Forbes contributor and science writer. He has written numerous books, including Beyond the Galaxy, How Humanity Looked Beyond Our Milky Way. His blog, Starts With a Bang, has won numerous awards and covers topics from black holes to time travel and everything in space. Ethan, welcome back to the show.
Thank you for having me, Dustin. It's my pleasure to be here, and I am so looking forward to sharing a little bit more science with your audience once again.
No, yeah, it was great. I really enjoyed our last episode, as did the audience from the feedback. And, I'd like to thank you for coming back on. And for those who may be listening for the first time, our first episode was episode 56. We covered a variety of topics from cosmic inflation to basically my own. I found out it was a 40-year-old misconception about the Big Bang. So I would encourage everybody to listen to that interview as well. But a topic we didn't get to was black holes. So I was actually wondering if we could just kind of start off with actually the background, the history of black holes. How were they kind of first conceived of, the science behind people or the individual who first kind of conceived of their actual existence, and moving on from there to the current date on what we know about them.
Well, in a crazy history lesson, it turns out that black holes, the history of them goes way back before Einstein's theory that predicts them. Way back in the 18th century, a scientist named John Mitchell was thinking about the sun, and he was thinking in particular about, like, what happened if I took the sun and I scaled it up. So he was imagining that you had an object that was the same density as the sun, but that you just imagined making it larger and larger and larger. And you know how density works, it's mass over volume. So if you double the radius of the sun, you're increasing its radius by a factor of 2, but its volume, and hence its mass, if the density is constant, is going up by a factor of 8. And what Mitchell calculated is that if you were to take the sun and expand it at the same density to be about 500 times its current size, it would be so massive in such a small volume of space that nothing, not even light, would be able to escape from it. That the escape velocity, or the speed that you'd calculate that you need to travel at in order to escape from the sun's gravitational pull, would actually be greater than the speed of light. So fast forward to the 1900s now, and Albert Einstein overthrows Newton's theory of gravity. He comes out with general relativity. This replaces Newton's instantaneous action at a distance force law with Einstein's field equations. And just a month or two after Einstein puts out his theory, Karl Schwarzschild, on close to the front lines in World War I, gets a hold of Einstein's paper, which I can only imagine Einstein's paper circulating through the World War I trenches, but there it is. And Schwarzschild, about a couple months later, comes up with this exact solution. And the exact solution he comes up with is known as the Schwarzschild solution, which is the solution for a non-rotating black hole in general relativity. It says that outside of this region of space called the event horizon, things can escape. That something that's outside the event horizon, if you put enough energy or speed into it and you accelerate it fast enough, it can escape from this object's gravitational pull. But once it crosses the event horizon, once it crosses over inside the event horizon, there's no way out. Everything that falls in when it will inevitably get dragged towards that singularity in the center of the black hole. That's where they first came from.
And for clarification, is the event horizon basically when they draw depictions? Because I think it was just this year, correct, that we got the first actual picture of a black hole or
Yeah, that is right. It was April, I believe, April 10th that they released it of this year. That was the first image of a black hole, which is kind of cool because that's 2 years almost exactly after they took the critical data, which was taken from April 5th through April 11th. That's when they took the data that allowed them to generate that image. And then 2 years later, this year, they actually released it.
And I'll link for the listeners that image, and I mean it's obviously not some 4K resolution up close picture or anything like that, but it very much looks kind of like the artistic depictions of it that you'll see of basically a very dark, lightless mass in the middle, surrounded by light around the edges. Is the event horizon basically what you can see surrounding it, and then once you cross it, or is the event horizon actually before that kind of swirling mass of light and whatever else has been caught up in it?
So the famous donut image that you're referring to, and literally scientists just call it the donut now, this has an event horizon inside of it. So there is a region in the middle where no light comes from, and that is the event horizon. But because in general relativity, the mass that you have there actually curves not just the space where the mass is, but the space around that mass. It turns out that what we see as where the dark spot is and where the light stuff is, the event horizon isn't the border between the dark stuff and the light stuff. It's actually smaller than that. It's actually inside of that. And the reason that such a large region of space appears dark is because of how severely space itself is curved. It's also worth pointing out that first solution I talked about by Carl Schwarzschild, that was discovered in 1916. It wasn't until the 1960s, almost half a century later, that someone discovered how you can write down a solution in Einstein's general relativity for a point mass that rotates. That's known as the Kerr solution, named after New Zealand physicist Roy Kerr. And Roy Kerr is still alive. And Roy Kerr, I think, is a shoo-in for the Nobel Prize if the Nobel Prize goes to this discovery, because without his work, we would not have the mathematical infrastructure we need to even make the predictions for what this black hole should have looked like.
And well, I guess we can get into the details here. I had a quick side note. I remember in elementary school, I became really obsessed with just space and everything like that. I'd gotten a pretty decent telescope for my 11th birthday, and one of my teachers just started giving me kind of all these articles and magazines relating to astronomy and everything like that. And I remembered that one of them was this article, and I don't know how true it was, so I was going to ask you about it. And it was basically kind of a story of them trying to describe what maybe it would be like, or what a black hole actually does, because the story was, if you were going feet first, kind of pushing the I believe button on this story of you going feet first into a black hole, and it was describing that basically the atoms, down to the atomic level, moving its way up your body, would just start to rip apart basically as the closer that you got to to the center of the black hole. And I understand it was a fanciful story, just trying to convey some very basic information to a younger audience, but I didn't know how realistic that is of the power of what we believe a black hole does.
Well, if you want the full answer to that, the answer is it depends on the black hole. And the reason it depends on the black hole is because if you were to take, say, the sun, and you were to compress all of the sun, all the atoms in it, all the particles in it, down into a single point, it would become a black hole. And it would become a black hole whose Schwarzschild radius, or who the size of the event horizon from the center to the edge of that event horizon, would be about 3 kilometers or so, would be about 3 kilometers. If you were to stand outside the edge of the event horizon of that black hole, have your feet on the edge of the event horizon and your head maybe, 1.5 to 2 meters above it, depending on how tall you are, you would notice something very uncomfortable happening to you because you know how gravity works, and the closer you are to an object, the bigger the gravitational force it exerts on you is, right? If you're twice as far away, the gravitational force is going to be only 1/4 as big in Newton's law, and in Einstein's theory, that difference is even more severe the closer you get to a large mass. So if you do this, if you were to do that experiment, you would find that your feet are closer to the center of the black hole than your head is, which means there would be a bigger force dragging your feet in than there is on the center of your body, and the force on the center of the body would be bigger than the force pulling your head in. So you would feel yourself getting stretched. Sorry about that. You would feel yourself getting stretched in the direction of the center of the black hole. We call this process of stretching you out in a line like that spaghettification, because it does. It takes a human sized object and stretches it thin into like a strand of spaghetti. Now, that's what happens if you go close to one of these low mass black holes. But the kind that we measured with the Event Horizon Telescope earlier this year, these are the other kind. These are supermassive black holes. So instead of having a mass that's a few times or 10 times or even a few dozen times the mass of our sun, we're talking about objects with millions or even billions of times the mass of our sun. The black hole that we took that famous image of earlier this year is 6.5 billion times the mass of the sun. If you were to do that, if you were to take your body and put, again, your feet at the edge of the event horizon and then your head 1.5 to 2 meters away, depending on how tall you were, this would be a force you'd barely be able to feel. It would be really no bigger than the force, the tidal forces that the moon exerts on you from planet Earth. It's pretty negligible. It's much less than 1 Newton, where a Newton is a unit of force that's even smaller than a pound. And so it depends which black hole you're talking about, what you observe. It is true that if you went to the center, the singularity, everything gets spaghettified. Everything inevitably falls towards the center of the black hole, and there's no way out. But if you're confining yourself to staying outside the event horizon, which I highly recommend if you ever want to go anywhere else other than the inside of this black hole, you're actually not going to feel that significant of a force outside of it compared to what's inside.
With everything that's being pulled in, I understand that it's all being. I guess my question would be is, usually in science fiction, they always, I mean, they take a lot of artistic license and everything like that. And black holes are usually kind of just easy throwaway object to throw in there and say, oh, well, they just, this black hole appears, they go through it, and then they come out on the other side of some, distant galaxy or fill in the blank, whatever plot hole that they need to fill. It's, with what do we know from what's been studied of black holes, or what is the current theory on where all that mass goes, that goes into the black hole?
Well, this is one of those instances where we really have to rely solely on theoretical physics because we don't have any observations that tell us what happens once you fall in. Once you fall into a black hole, that information doesn't come back out. That information isn't something we can access. So all we have are theoretical calculations. And with the theoretical calculations we can do, there are a few different possibilities. We know from general relativity alone, from just pure, plain old general relativity, it predicts what we call a singularity at the center, which is to say, when you start calculating, okay, this mass falls inside, and what does it do? And the answer is there's no force. And maybe a good way to think about this is if you imagine how does a force work, you can view it as any two particles in the universe can exchange information. Like if I'm an electron and you're an electron, I can send you a photon and you'll receive that photon. And when I send it and you receive it, that makes a repulsive force between us because we have the same sign charge. If I'm an electron and you're a proton, I would send a photon and you would absorb that photon, and we would both be attracted to each other because that's how the electromagnetic force works. Well, in gravity, you know, anything we can imagine, if you tried to send a signal from the central singularity outward, it wouldn't go anywhere because everything from that central singularity has to go to the central singularity. So there's no way for something inside a black hole to exert a force on something that's farther out. So that's what we're stuck with in general relativity is all we have the mass of the black hole, we know it can spin, that's the angular momentum that Kerr added in. I guess it could have charge, right? I could fill my black hole full of protons but not electrons and give it a charge. That's it. Those are the only things that determine the shape of the singularity. For the black holes we typically talk about, a Schwarzschild black hole, one that doesn't spin, its singularity will be a point at the center. But for a spinning black hole, its singularity is actually going to be smeared out into a one-dimensional loop, into a ring-like shape. And what's interesting here is some people have calculated if you were to fall into a black hole, what would you see? And the answer is you'd never be able to observe yourself hitting the singularity. That as you fell in and went closer and closer and closer to that black hole, time would asymptotically stop passing for you. And this is where people debate over what happens. Does this black hole lead you to a singularity anyway, and you just get crushed and there's nothing else? Or does this black hole get connected somewhere else? Will it lead you to the birth of a new universe? Will it lead you to a white hole somewhere else in the universe? Is there some way to stabilize the inside of a black hole and have this actually function more like a wormhole than anything else? The last few options I gave you are probably more speculation than grounded in physics, but it's important to keep our mind open to all the possibilities in the absence of knowing the answer to the question.
Well, if some of the latter ones that you mentioned, as far as for like a light hole or something like that, I would imagine that this implies that the matter that is being sucked into the black hole is being spewed out somewhere else. So, would it not technically wouldn't we have seen something if these did exist, or maybe they're just so rare, I don't know, that they're, or like you said, going into another separate universe. But if they did spit out somewhere within ours, wouldn't we be able to view that in some way to confirm it, and that the lack of confirmation kind of disproved this, at least of spewing out somewhere within our universe, and only leave it up to somewhere outside of our understanding, to where these lead out, if that's true?
I think that's probably fair to say that the white hole option, where white is the opposite of black, that a black hole is, they view them as the time reverse of one another. where a black hole is all the matter falls in and nothing gets out. A white hole would be the opposite, a place where nothing falls in and things just exited it. You're right, we don't see that. However, there are some people who argue that our universe does have one white hole in it, or at least it did 13.8 billion years ago, and that's what the Big Bang was. Now, that's a very controversial opinion, but there are people who have that opinion, and it isn't crazy to think that. It's not a mainstream idea, but it is something that we can't theoretically rule out. So you're right, it's pretty clear that the black holes we have in our universe are not also connected to white holes that are visible in our observable universe. But that doesn't necessarily mean that there isn't a connection between black holes, which are very real, and the theoretical counterpart of them, white holes, which may or may not be real.
And that this concept of the bending of space time, and the more I read about these concepts, it seems to me that time and the way that we've thought about it for all of human history is just a really bad way of measurement. If it can be, I wouldn't use the word corrupted, but um, where if you're actually being sucked in or caught within the event horizon of a black hole, or approaching it where it's bending space-time, or I mean any celestial body does that to an extent, it's really hard for my monkey brain to conceive of, or even when they talk about traveling at the speed of light, that you are going to experience time at a different measure than people that you say left behind on Earth or wherever you came from. It's a very strange concept to me, and you know because if you think about time as being this measurement, if it can be bent, then would it be better to explain it as more of, I don't know, like a thing of itself versus a or a force that can be changed more than this static sort of thing that we conceive of it.
Well, I would maybe encourage you, if that was the route you wanted to go down conceptually, I'd encourage you to think about this word space-time that we use, because I know you have this idea in your head of what space is, right? Maybe you imagine like a three-dimensional Cartesian grid or coordinate system, and maybe for time you imagine something like a clock just ticking, tick, 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 no matter where you go. Now, if you and I were in the same place and we were both at rest with respect to each other, we're at the same place, the same time, we've got the same motion through space, we would absolutely agree on everything. We would agree on space and we would agree on time. But now, let's imagine, for a nice, fun sci fi scenario, let's imagine that you're going to go on a trip, that we have procured an extremely fast rocket ship that can travel at more than 99% the speed of light. And we're going to send you on a fantastic journey to go visit the Trappist 1 solar system. Trappist 1 is a red dwarf located 40 light years away, and it has at least 7 rocky terrestrial like planets orbiting it. It is one of the most fascinating exoplanet systems we've ever discovered. So good job, Dustin. You get to go. I get to stay behind. You get to go. If you get in that rocket ship and you travel there very close to the speed of light, I might see that it takes you 40 years and 6 months to get there. From my point of view, you leave, you're traveling close to, but not quite at the speed of light. And so if I sent a light beam at the same time you left, the light beam would beat you there, from my perspective, by 6 months. You get there, you take your pictures, you turn around, you come back. Another 40 years and 6 months pass, so a total of 81 years later. And I'm 41 now, so you get back and I'm 122 years old. But how old are you going to be? Well, however old you are now, what I see for you as a journey of 40 years and 6 months, you will only perceive as a journey of 6 months. And the reason for that is you are moving so close to the speed of light that you suffer two effects. You suffer the effects of length contraction, which means in the direction that you move, distances seem shorter. And you also suffer the effects of time dilation, which means your clock runs at a different rate than my clock due to your motion. The thing you have to remember, the reason we call it space time is because you always move through space time. When we are staying still, we're not moving through space, and that means 100% of our motion is through time. But when you're in motion, when you're accelerating, when you're moving close to the speed of light relative to something else, you see distances are shorter and your clocks run differently too. So you travel there close to the speed of light. It doesn't look like 40 light years to you. It looks like a much shorter distance. Only 6 months pass and you arrive. You turn around, you do the reverse voyage, and whereas I will have aged 81 years, you will have only aged 1 year. Now, that's special relativity. That doesn't take into account gravity. But what you have to remember, this was the biggest idea, according to Einstein, of Einstein's life. He called it the equivalence principle. And what he realized is that any acceleration that you experience is indistinguishable from any other form of acceleration. So if you turn on that rocket and you speed towards the Trappist 1 system, and then you turn on the rocket in the other direction and you speed back home, that's no different than experiencing that same acceleration as though it were due to gravity. So I view the space around a black hole the same way you might view a moving walkway or being in a river that has a very strong current. There's something trying to drag you into the black hole. It's like the space beneath your feet or your spaceship is actually moving, is accelerating you towards that central singularity. So you need to fight that somehow. You need to keep yourself from being dragged in. And that takes energy. That requires you to accelerate. But that also explains why when you are near a black hole's event horizon, space gets distorted and also your clocks get distorted as well. That's a feature that the movie Interstellar got right. That when you go very close towards the event horizon of a black hole, when you get very close there, your clock will actually run at a very different rate than someone not near that black hole. So if you spend even a short amount of time in the strong gravitational field of a black hole and then you come back out, you will have discovered that the universe around you will have aged much more severely than you have.
Yeah, because I was going to ask you, it's one of my, I like any movie that even if it takes a lot of artistic license, it really kind of um, shows the just kind of the how vast space is. And I think that this is really with like Interstellar or Gravity on the big screen. I think it really kind of helps to do that. And I was actually going to ask you how obviously there's a lot of different stuff within that movie, but I'm glad that was pretty accurate within that context. What would you say is probably the most, or in your opinion, the most accurate in either science fiction series or movie that kind of really depicts, space really, and what we know about space, or at least what we knew at the time, really accurately?
Well, when you talk about movies in outer space that get it right, Interstellar does get some things right, but they also add in some speculative things. Same with a movie like Contact, which I very much enjoyed, but the things it adds in about space, they're also pretty speculative. Something like Gravity, they get many of the details right, but they get many of them wrong. I don't know why Sandra Bullock's hair always looks as though it has gravity when it super doesn't. There are some wonderful videos you can Google of astronaut Karen Nyberg washing her hair in space, and you can see that, yeah, you put Sandra Bullock up there for 10 minutes and there's no way her hair will ever look like it does in the movie again. But when it comes to what movies get space really right, there are some rules that things follow in space that aren't really depicted that well. Uh, I think looking at some of the scenes that get it wrong from classic movies are maybe more informative to me. When you see the Death Star blow up in Star Wars and you hear that enormous explosion, no, there isn't a medium for sound to travel through in space. And the shock wave, when it arrives at your ship, that might rock the ship and make a sound, but you're not going to hear that, compression rarefaction effect that makes a sound wave. That doesn't travel. Also, not to pick on Star Wars, but to pick on Star Wars a little bit. um, One of the things that always bothers me is when something is traveling in a straight line through space and it gets hit and its engines give out. All of a sudden the thing just slows down and comes to rest. That's not how the conservation of momentum works. When you are traveling through space in a straight line and something gets hit, it's going to keep moving in that same straight line because there's nothing in space to change its momentum. There's no drag force or no air resistance. There's nothing to slow you down. So I'll say, if you want things that work hard to get the science of space travel right, you'll really want to stick to the harder sci-fi. Some of the Star Trek films do a good job with that. Interstellar does a pretty good job with that. I actually liked it. I haven't seen the movie version, but I have read the books, and I think that Ender's Game and Speaker for the Dead, they do a really good job taking care to get that right. But the big question of, is there a movie that really just gets every one of the details right? It's tough to remember that, you know, if we made a scientifically accurate movie about space travel, chances are it would be a pretty boring movie. And that's maybe one of the reasons that we haven't aimed humanity towards interstellar destinations just yet.
Well, and going back to your discussion on bending of space time when you're traveling at or approaching the speed of light, what always got me in Star Trek, because it came on Netflix, and just out of nostalgia, I was watching Next Generation episodes that I'd watched as a kid, and going at the speeds that they were, it always, knowing a little bit more than I did when I was 12 years old, as I was going, well, they're traveling across these vast distances at very high speeds, but whenever they get back, it's that star base still has the same people on it and all that. Whereas, as you were explaining, if they traveled back to Earth after, being out in space for a couple of years, traveling across the galaxy, those people's lives would be, whether it's Earth or a star base or wherever, would be have the time would have moved quite differently for them. And obviously that doesn't make for good television if every time they go back home everybody's dead. But that is interesting, that you mentioned that maybe people wouldn't be as interested if we got everything right. And that probably goes for pretty much anything that we want to make cinema about.
Yeah, and you want, for me, from a science perspective, I'm always going to be interested in a movie, in the characters, in the plot, in all the interesting things that come about from that. But I want them to get the science right. There's a difference to me between, you know, a hard a science fiction film that struggles to get the details right and takes that care, and what I would call a space fantasy or space opera, some people call it, where, okay, I really just want to tell an adventure story and have it be set in space. And there's nothing wrong with that. There's nothing wrong with having that be the kind of film you enjoy. But I think if that's the kind of film you want, you're probably less likely to have it grounded in that hard science. Firefly is a great example of a series that I loved, that is a space fantasy series. And they might get a few of the traveling through space details right, But if something needs to be sacrificed in order to have the plot work better, they're going to sacrifice it so that the plot works better, and that's fine. The only thing that ever really bothers me about a sci-fi series is when they state up front what the rules of their universe are and how those rules are different than ours, and then they break those rules because they want something else to happen. That's usually the main thing that'll bother me.
The canceling of Firefly, I think, was one of the great tragedies of science fiction. I'm glad they tied it up with a movie, but just as a side note, I hadn't seen it when it first came out, and I think it was on a Netflix or Amazon Prime or something like that. And I stumbled on it, not realizing it was only like a season and a half, and that was just it was really sad to me when I found out that it had been canceled like 5 years before that. But I take your point as well. And I was just thinking about it's not necessarily a science that they're stating at the beginning, but something like in Star Trek with the Prime Directive, where they state that as being the most important directive that they have, and then they break it every single chance that they get. But yeah, it is a little bit disconcerting when they kind of paint a universe. You need to push that "I believe" button, and then they just kind of just go with whatever fits the storyline.
Yeah, I mean, and that's the whole thing is I think that there are a few instances where knowing some physics has really you know has really disrupted my enjoyment of a film because I can't stop thinking about these details that they get egregiously wrong. But most of the time, that doesn't occur. Most of the time, I'm just, if it's a good film, if it's an enjoyable film, I'll enjoy the film. I don't want to Neil deGrasse Tyson anyone and sort of like pick holes and like, oh, the earth doesn't rotate that way and things are counterclockwise and not clockwise. Like, no, like those are not the important details to get right. It might be amusing to some to have like the discrepancies pointed out like that, but I'd rather just enjoy the film. If you want to know if it's accurate or not, we could talk about if it's accurate or not. But accurate science in your science fiction doesn't necessarily make for a better film, and inaccurate science often makes for a much better film. I could go on all day talking about the physics impossibilities of almost everything in the Marvel Cinematic Universe. But that's not the point of the Marvel Cinematic Universe. The point is to have a fun superhero story that everyone can enjoy. And at that, I think those movies are very successful.
Now, I was just actually reading a article. I think it just came out within the last week. It was on Astronomy magazine, and they were talking about how the Milky Way may have two supermassive black holes at the center of it, and we also, if I'm not incorrect, that every universe, or not every universe, every galaxy, they believe actually has a black hole at the center. Is that correct?
Most of them.
Okay.
Sometimes two galaxies will merge or interact or pass close by one another. And when that happens, it's possible for one of those supermassive black holes that were at the center of that galaxy to actually get kicked out of it. And we've seen that happen before. We've seen a black hole on its way out of the galaxy that has, millions of times or more the mass of our sun. So we think on average, for all intents and purposes, yeah, every large galaxy should have a supermassive black hole at its center. But, we have some 2 trillion galaxies in the universe, and I'll pretty much guarantee you that there are exceptions.
And what they were saying in that article is that, because galaxies will collide, and maybe this is what you're talking about with them getting kicked out, but if these two supermassive black holes are basically kind of like sisters together in the middle of this galaxy, how what kind of forces are they exerting on each other, and how do they? I mean, I know this sounds very like a basic question, but would one of them suck the other one into it, or are they almost repellent of each other, slowly moving away, or do they just kind of basically kind of stay the same distance apart? What kind of forces are they playing with each other
So
What will happen eventually?
this is actually a really deep question, and so good for you for going all the way and asking it, because what we're talking about here is when you have two large masses near the center of a galaxy, they're going to exert a gravitational force on each other. They're going to curve space-time, and they're going to orbit each other and emit gravitational radiation, so that those orbits will eventually decay. But for some of those black holes we have, for some of those configurations we have, it's going to take much longer than the current age of the universe for that process to happen. There is, however, a big thing that can accelerate that, and that is when you start asking the question of, but what about all the other masses there? We have stars, we have planets, we have asteroids, we have failed stars known as brown dwarfs, we have clouds of dust and gas and plasma. And all of these forms of matter are also going to gravitationally interact. There is a subtle but very consistent phenomenon, and I'm going to teach you a little word here. It's a lot of fun. I like it. It's a kind of an oxymoron. It's called violent relaxation. And what it basically says is if you have a couple of large masses orbiting each other, and then you have smaller masses nearby, what's going to happen due to gravitational interactions is these small masses are going to get kicked out. They're going to get a big gravitational kick applied to them, but because of conservation of energy, if you give something a lot of energy, something else has to lose energy. It's going to be the orbits between those two big masses. So if we had two supermassive black holes at the center of our galaxy, what would happen over time is all these stars that pass by, they would get kicked. They would get this extra amount of momentum plugged into them. Many of them would get kicked out of the galaxy entirely, while all the while, with every little kick that happens to one of those stars or stellar remnants or failed stars, those two central black holes would get closer and closer and closer. So there's a critical time scale depending on how massive these black holes are, how far apart they start, and what the rate of interacting with other stuff is, that's going to determine, okay, how long is it going to take for these two objects to in spiral and fall into each other. The article you read in Astronomy magazine, it's a real possibility. It's based on a real scientific paper. At this point, I would say the evidence supporting it is relatively flimsy, but that doesn't mean it isn't going to be right in the long run. It just means that looking at the evidence we have, it is not enough to conclude. It's not strong enough to conclude that, yeah, there are two black holes there. Everything, or almost everything, is very consistent with there being just one mass. And the best evidence we have is to look at the individual orbits of the stars that seem to go around that black hole, and they do appear to behave just as though it's one mass, not two.
And with the, at the center of, let's say, our own, or the Milky Way galaxy, the black hole, or possibly two that are there, and they are their gravitational pull is pulling in all this mass. The closer star systems and everything like that are being pulled into it. Is this like the theory of it eventually pulling everything into it, or is there, like outside of the event horizon, where there's a certain point where the galaxy just keeps on spinning and eventually just be a larger black spot, and then it doesn't have any more pull, or is it, as it's pulling in more mass, it just becomes, it exerts even more of a gravitational pull, and eventually will pull everything into it? Of course, our sun will be gone by the time that would ever happen, but just in kind of a long enough timeline.
So, if you want to know about the far, far future of things, you have to look at what processes occur fastest, what's most efficient. If you said, hey, Ethan, can you do the calculation of how long it would take the Earth to spiral into the sun just from gravitational waves? Yeah, we can do that. You'll get something like 10 to the 26 years. And that's much longer than the age of the universe, which is 10 to the 10 years. like 1.4 times 10 to the 10 years. So you say, oh, yeah, like the sun will be gone by then. Probably other things will have happened. But when you start asking, what are the other things that happen, right? Because you would think, oh, well, you have the sun and the stars, and they'll all live and die, and they'll all fall into that black hole eventually. It turns out that with billions or hundreds of billions or trillions of objects like the sun in your galaxy, they're going to pass by one another randomly over time. And when they do, like all objects, they'll gravitationally kick each other. Some of them will get directed more towards the center of the galaxy, some of them will get kicked outward. The ones that get migrated towards the center of the galaxy will tend to be the more massive one, and those will be the things that tend to get devoured by the black hole eventually. Other objects, the lighter mass ones, they'll tend to get kicked out. So when you look at a universe that's about 10 million, 100 million, maybe even a billion times the age of our universe now, you'll find that most of the masses, including our sun, will probably get kicked out of the galaxy, and only a small fraction of a percentage of these objects will actually wind up funneled into the black hole at the center.
So it is true when they say that basically we are kind of basically on our own spaceship, just flying through space. Eventually you're just you're getting whipped around this thing, and will get flung out at some point if you stay on the spaceship Earth.
Yeah, and it's really interesting because we still don't know. Here at the end of 2019, we still don't know what the fate of the Earth is. We know in about 7 billion years or so, our sun will swell and become a red giant and start fusing helium in its core, and it's going to devour Mercury and it's going to devour Venus. And nobody knows whether it will devour Earth or not. There is conflicting research on that, even since 2008, which is when the most recent, like, definitive paper came out, and it's since been challenged. We don't know whether when the sun becomes a red giant, it will swallow Earth. If it does, then that's going to be the end of the Earth. But if not, then Earth will become the innermost planet in our solar system once the sun becomes a white dwarf. And when our sun eventually gets kicked out of the galaxy, which is, there's over a 99% chance that that's what's going to happen, we don't know whether that interaction that does it will keep Earth bound to the sun, or whether there will be another interaction or a different interaction that actually kicks the Earth out and leaves the remnants of the sun intact. So we don't know whether we're going to have a remnant of our sun to orbit for the indefinite future until we spiral into it from gravitational waves, or whether when the sun becomes a red giant, if it'll eat us, or whether we'll stay bound to the sun's remnant or get kicked out of it. All of these are not yet questions that we know enough about the universe to give a definitive answer to. These are just the possibilities.
And is there, being mindful of your time, is there anything else about black holes and their effect and interactions within the universe? I guess, you know, I was going to ask you earlier on, kind of badly worded, of the purpose of a black hole, but there's not a purpose. Things just are as they are. But you know, do you view them, or are they viewed as kind of integral to how the universe functions? Or I guess you could say, if one of those theories is correct, that it actually does shoot out and create another Big Bang for another universe. What kind of, I guess I don't really know how to word it, but what kind of, I guess I'm just going to use the word purpose. What purpose do they actually serve within the universe, as far as for, continuing either the expansion or the cosmic inflation, or are they just the same as like a planet or a star, an asteroid, of just kind of one of these things that exist within the larger universe?
So I think what you're trying to ask is, if our universe didn't have any black holes in it, would it be different than the universe we have? And if so, how? And if you were to say, oh, our universe doesn't have any black holes, what does it look like? I think it would look almost indistinguishable from the universe today. Now, a few things would be different. We wouldn't see active galactic nuclei. We wouldn't see galaxies spitting out these enormous jets when matter falls into them, because those are driven by the supermassive black holes at their center. We wouldn't have the objects known as quasars, because those are powered by black holes. Within our own galaxy, we wouldn't have phenomena known as microquasars, which are stellar mass black holes that absorb matter, feed on matter, they turn on, they turn off, they emit jets, the jets turn off. We wouldn't have those. We wouldn't have neutron star mergers work the way they do, because when we had in 2017 that big detection of two neutron stars that merged together, all the indications were that they formed a black hole. And that's where we get the heaviest elements in our universe. So there would have to be something else that happened, or we'd have to get our heavy elements from somewhere else. Same deal with the most massive core collapse supernovae. When you get core collapse supernovae, it'll either produce a neutron star or a black hole. And if black holes were forbidden, there would be something else that they would have to produce that we don't quite know. One of the most interesting theoretical possibilities is, this is one I've actually worked on some, so I might be a little biased towards it, or in this case against it. Some people have suggested that it is only the formation of black holes, objects this dense that collapse down to a singularity, that have an overall effect on the universe that turns out to be responsible for the dark energy we see. And that's an interesting idea. When you explore it in detail, you can look at the gravitational binding energy that exists within black holes, and you can compare it to the energy density of dark energy, and it's off by a lot. It's off by around a factor of 1,000,000 or so, which is why I think it's unlikely. But if dark energy, if this accelerated expansion of the universe, which we don't know its cause, comes about because of black holes, that's a possibility we haven't ruled out. And that could be a fascinating consequence to having black holes in the universe. But other than just being an end state to certain phases in stellar evolution or gravitational collapse, I don't know of a purpose that black holes necessarily serve for the universe. All I can do is give you the ideas that the best minds have come up with the best constraints that we have working in this area.
Well, I'd like to thank you for coming back on and giving us all this information. I thoroughly enjoyed it, and I was wondering how people can consume your content, get in touch with you, and just generally keep up with what you're doing.
Sure. Well, I'm Ethan Siegel, and I'm known online as Starts with a Bang. I've got a Facebook page, Starts with a Bang, a Tumblr, Starts with a Bang, a Twitter at Starts with a Bang, and I run the Starts with a Bang Starts with a Bang blog on Forbes. I have a Patreon where I create science stories, and I run the Starts with a Bang podcast on SoundCloud. So if you want to get in touch with me, think Starts with a Bang, and if you have any questions that you want me to take a look at, I do a weekly Ask Ethan column, and you can send in your questions to startswithabang@gmail.com.
Well, thanks again, and I will have all the contact information as well as the articles and everything that we mentioned in the show notes at didyouknowcrypto.com/EP65. That's EP65 for episode 65. And once again, thank you very much.
My pleasure. Thank you for having me.